continuing from mass spectroscopy. We're not going to talk about mass spectroscopy at the moment. What we're going to talk about is it's going to be called NMR now. As a mass spectroscopy and NMR, they go hand in hand. Mass spectroscopy से हमें दो तीन चीजें पता लगी थी कि I told you कि if you मतलब उसकी भी क्विक रिकैप कर लें कि I told you कि mass spectroscopy के अंदर you would get heavy particles which would be your molecular ions and you will get all these fragments. ठीक है, fragments से you get some information about the structure or the types of structure in a particular molecule. But like for example 28 आ रहा है तो you can guess कि there would be two nitrogens or there might be a carbon attached to an oxygen. So you get all these tiny fragments. फिर आपको number of carbon atoms पता लगते थे, number of chlorines पता लगते थे, number of bromines because of the isotopes. You would look at the M plus 2 ratio which is given over here. If there's one Cl, if there are two Cls, the M plus 2, M plus 4 ratios, okay, the molecular ion mass could change because of the isotopes. They could become heavy or they could become light. And similarly, you had कि bromine की mass spectroscopy थी यहाँ पे summary लिखी होगी ठीक है this is what the summary is of the whole thing. Now you could check whether a molecule has one bromine or two bromines etc. And then you could also check how many number of carbon atoms it has because carbon had an isotope as well and you can figure out the number of mainly ये दो चीजें थी mainly. And we also, I think, did okay, if a molecule has one chlorine and one bromine. This one as well. कि हमने इसकी भी probabilities हमने figure out की थी कि what happens if a molecule has one chlorine and one bromine. ठीक है, all of a sudden, just a second. तो ये भी important था कि this has been asked as a question as well. So ये सारा तो mass spectroscopy तो fragments से आपको you got some information about what the structure of the molecule is. Now something that is very different from mass spectroscopy, but is an analytical technique that is usually used alongside mass spectroscopy. We can't do mass spectroscopy past papers unless we do this other technique. Now this other technique is known as nuclear magnetic resonance. It's it's probably one of the most powerful techniques out there of analyzing molecules. It's called nuclear magnetic resonance, or in short, it's known as NMR. Okay, so mass spectroscopy was kind of very limited. Okay, you just figure out a few things: number of carbon atoms, number of chlorines, number of bromines. Now, what you couldn't figure out was okay, how were they arranged. Okay, your fragments gave you some information, but not all of it. I said NMR. What does NMR do? The first thing is there's a carbon 13 NMR and there's a hydrogen NMR. Right now we're talking about the H11 NMR. Okay, this is what we're studying. Now, starting from the very basic, the first thing is that almost all elements, I mean, not almost all elements have nucleons. Okay, they have a nucleus, all of them. And the nucleus contains protons and neutrons. These are your particles that exist in the nucleus of an atom. Okay? And the electrons are surrounding this nucleus. Now, I'm not interested in the electrons at the moment. Okay? So I'm only interested in the nucleus at the moment. Now, all these elementary particles, they come with the magnetic field. Now I'm going to be calling them nucleons now. It contains nucleons. Now, when it comes to charge, the protons and neutrons have a very different charge. Like protons are +1, neutrons they don't have any charge. But all elementary particles, they have a magnetic field, and so do your nucleons. So remember, when it comes to magnetic field, I'm not really differentiating between what a proton is and what a neutron is, because the magnetic fields are kind of similar. So nucleons have magnetic dipole moments, or you can call them magnetic spins. So they have magnetic dipole moment or spins, which are paired. What that basically means is you did pairing of spins in orbitals as well. Magnetic fields are usually paired, and they are oppositely paired. The reason they are oppositely paired is because you want the magnetic fields of the particles to be attracting each other. For example, if there's a nucleus over here, all elementary particles, protons, neutrons, and electrons, they have their magnetic fields, which we don't usually study about. So if here's one nucleon and here's another nucleon. Okay? Remember, I'm not differentiating between what a proton and between a proton and a neutron. They almost have the same type of magnetic fields. So if this particle in the nucleus, it has a magnetic field that is an upward spin. For example, the magnetic field is pointing upwards. The other one is going to have a magnetic field that would be pointing in the downward direction, because you want the two particles to attract each other. That's the only way they can attract each other, if they have opposite magnetic fields. Then they would be paired and they would be able to attract each other in the nucleus. Is this clear? The first thing, every particle has a magnetic field, and the magnetic fields are paired, just like electrons in an orbital. Is this clear, Sarah? Is this clear? Uh, Aisha,
Mm, yes, sir.
Rafika, Burera, clear?
Yes.
Yes, sir.
I just so if a nucleus has a lot of nucleons, for example, you have a carbon. Uh, let's think of a carbon 12 nucleus. Now it's going to have six protons and six neutrons. So that basically means that's the nucleus. So in total, there are 12 nucleons. Now, all 12 of them are going to be paired in the nucleus. Like if one is upward, the other one next to it would be downward. If one has upward spin, the other one has magnetic field pointing downwards. So there would be six pairs of nucleons all paired together. That would give you 12 nucleons. So that's 3, 4, 5, and that's the sixth pair. Now, because of this, the carbon nucleus is not going to have an overall magnetic field, because the magnetic fields are canceling each other out. Uh, Even if an atom has two nucleons, uh, the magnetic dipoles or spins, they cancel each other out. Because if one is pointing upwards, the other one is pointing downwards, which means that their effects are completely cancelled out. And the atom or the nucleus would not exhibit any magnetic field. So if you have 12 nucleons, all of them are going to be paired. And the overall effect is there's not going to be any net dipole. No net dipole is going to exist.
सर अगर odd number हो
हाँ, उस पे मैं आ रहा हूँ. ठीक है, so the atom is going to be magnetically, it's going to be neutral. It's not going to have a magnetic field. अच्छा, तो odd number का ये कि if an element has if an element has an odd number of nucleons, तो then there would be a net magnetic field. इसीलिए आपके कुछ atoms होते हैं, elements होते हैं, वो magnetic होते हैं, क्योंकि उनकी magnetic fields, it's not getting paired, it's not getting cancelled out. So if an element has an odd number of nucleons, then its nucleus will exhibit an overall magnetic spin. So there's going to be an overall magnetic spin. And the first example that we're going to do is the hydrogen nucleus. Hydrogen is 1 and 1, which means it has no neutrons. Those kinds of nucleus होगा ना, if you look at the nucleus of a hydrogen atom, it only has one proton. Now, if it only has one proton, that one proton has a particular magnetic field. Let's say it's pointing in this direction. So this would be the magnetic dipole. So the hydrogen atom would be acting as a tiny magnet. It would have a magnetic field. I mean, this would be the north. Magnetic field lines would be coming out of the north and they would be going into the south, just like a magnet. ठीक है, for example, if I show you किससे होता है magnet, ठीक है, for example, this one. So the hydrogen nucleus would be kind of like this. But it would have north and south poles. The magnetic field lines would be coming out of one side and going into the other side. So that's the reason why some elements are magnetic, because the magnetic fields are not getting paired because they have an odd number of nucleons. And on its own, think of a hydrogen atom as a small compass needle. It could point in any direction, wherever it likes. उसका arrow उधर रह गया, just a second. अच्छा, so it could point basically in any direction, wherever you. It's like a magnet that could be placed in any direction. ठीक है? Is this point clear so far?
Yes.
ठीक है? Ali, is this clear,
Yes.
Sara? अच्छा.
Yes, sir.
Okay. अच्छा, now the thing is. अच्छा, now the thing is, most of the common elements they don't have magnetic fields. ठीक है? Most common elements that you observe, I mean, that are common basically, that exist in atoms, like carbon, oxygen, nitrogen, etc. A lot of common elements have paired spins. Because their nucleons are even. ठीक है? Carbon is 12, oxygen is 16, nitrogen is 14. So most of them are paired, which is why they don't exhibit they don't exhibit any sort of magnetism. Achha, why is hydrogen important? The reason hydrogen is important, especially in organic chemistry. So in organic chem, hydrogen atoms are present almost everywhere in a molecule. ठीक है? They're almost present everywhere. They're always there. So to analyze how hydrogen atoms would behave under a magnetic field, that would give us a lot of information about the organic molecule. So what we're going to do is, let's think of a CH4 molecule. So let's think of a CH4 molecule, and each hydrogen atom or its nucleus would be behaving would have a magnetic field. It would be behaving as a tiny magnet. But right now, the magnetic fields could be pointing in any direction. You can think of 4 magnets, and they are randomly oriented. in any direction. I mean, right now they don't have. I mean, if you think of an isolated magnet, that magnet could be anywhere, pointing anywhere. So there would be four hydrogen atoms, and their magnetic fields are pointing in any direction, randomly pointing towards any direction. Okay. Is this clear so far? Ariba, is this clear?
Yes, sir.
अच्छा उसके बाद what you do is if you have looked at MRI scanners, you would notice that MRI scanners are basically these giant magnets. I mean, they're circular giant magnets. And they have a north pole and they have a south pole. Okay, so imagine that you have placed these tiny magnets. Think of the hydrogen atom as these tiny compass needles. And you've all of a sudden placed them in this powerful external magnetic field. Okay, so this is your powerful external magnetic field. ये मैं शो भी कर देता हूँ कि किधर है हमारे ठीक है if you can see an image तो it's basically this कि आप ना एक इंसान को ना you take a human and you place it this is this powerful external magnetic field अच्छा just one second मैंने कहा शायद नहीं आ रही just hold on one second अच्छा चलो ये फिर से कि आवाज आ गई अली
जी सर ठीक है
अच्छा ये हमारे स्कैनर है ठीक है दिस इज द पावरफुल एक्सटर्नल मैग्नेटिक फील्ड तो उसके अंदर ना इस मॉलिक्यूल को इट हैज बीन प्लेस्ड मॉलिक्यूल को क्या प्लेस किया उसको आई मीन द होल मतलब फॉर एग्जांपल एनी अभी तो मॉलिक्यूल्स की कर रहे हैं ठीक है सो मॉलिक्यूल इज प्लेस्ड इन दिस पावरफुल एक्सटर्नल मैग्नेटिक फील्ड एंड व्हेन इट इज प्लेस्ड इन दैट मैग्नेटिक फील्ड तो व्हाट हैपेंस कंपास की नीडल्स किधर पॉइंट कर रही होती हैं यूजुअली आप कंपास खरीदते हो वेयर आर दे पॉइंटिंग
North.
ठीक है नॉर्थ तो एक्सटर्नल मैग्नेटिक फील्ड यहाँ पे आपने एक पावरफुल उधर अर्थ की एक्सटर्नल मैग्नेटिक फील्ड होती है यहाँ पे व्हाट यू हैव डन है इसके आपने इसकी रखती है मैग्नेट्स रखती हैं पावरफुल सो ऑल दीज hydrogen atoms they start pointing they start pointing towards this powerful external magnetic field all of them ठीक है all of them they start pointing towards this external magnetic field तो जैसा कंपास की नीडल अलाइन कर जाती है अर्थ के साथ ना उस तरह अब फॉर एग्जांपल ह्यूमन बॉडी रखी है उसके अंदर तो दैट्स ऑल योर हाइड्रोजन प्रोटॉन्स are now pointing the magnetic field are now pointing in the direction of the north to south ही होती है ना magnetic field physics में क्या होता है यही होता है मेरे ख्याल से so all the hydrogen protons they start pointing towards the south towards this external magnetic field this is known as the low energy state ठीक है that's a low energy state और low energy state जो है that's basically why is it called the low energy state क्योंकि by default all your hydrogen protons are going to point in this direction ठीक है क्योंकि let's say they are not energetic and जहां पे भी I mean if you take a compass needle तो वो by default north की तरफ point करती है that's a low energy state because it is very hard for them to point in the opposite direction but it's very hard for us to make it point I mean it has to be very energetic so that it's capable of opposing the external magnetic field मतलब कंपास की जो नीडल है उसको ऑपोजिट डायरेक्शन में पॉइंट कराना है तो आपको हाथ से पकड़ के एनर्जी अप्लाई करके उसको जबरदस्ती ऑपोजिट डायरेक्शन में पॉइंट कराना पड़ेगा, ठीक है? सो दैट्स I mean, you would have to apply energy to make it point in the opposite direction. Now, the way you give these hydrogen protons energy is through radio frequencies. Okay, there would be lots of radio waves that would be making. So there would be lots of radio waves that would be providing energy to these hydrogen protons. And these hydrogen protons, if they become energetic, they go into a high energy state. They start opposing the external magnetic field. Okay, so all of them, they would become energetic, and they would start to oppose the external magnetic field. So what happens is, इसको यहाँ पे रख लेते हैं. So right now they're at the low energy state, which is known as the aligned spin. And then they go into the opposing spin, which is known as the high energy state, or also known as the opposing spin. Is this idea clear? ये सारा clear है, Reba, Ali, Abu Rara, is this clear?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
अच्छा, अब ये कि so this is known as resonance. ठीक है, MRI के अंदर ना resonance is this thing कि your hydrogen protons would be resonating. ठीक है, for example, if you put an if you put a human in an MRI scanner, तो मतलब your hydrogen protons, for example, ये जो भी है, ठीक है, if you're in an MRI scanner, your hydrogen protons, जितने भी protons होंगे, वो aligned होंगे external magnetic field से, and as soon as you start emitting these radio frequencies, they would become energetic and they would start opposing the external magnetic field. The good thing is कि unlike macro level के ऊपर ना, ये quantum level के ऊपर, there are only two states that exist. There's a high energy state and there's a low energy state. There's an aligned spin and there's an opposing spin. That's it. मतलब ये कभी भी नहीं होता at the subatomic level. Subatomic level के ऊपर the energy states are very discrete. जिस तरह shells होते हैं, subshells होते हैं, they're all very very discrete, which means कि it's not कि they can exist in any state. The states are very limited at the subatomic level. मतलब ये नहीं होगा कि बीच में ना इस तरह करके your hydrogen proton is stuck somewhere in the middle. That's not going to happen. ठीक है? It's either going to be aligned with the external magnetic field, or it's going to be in the opposing spin. ठीक है? There would be only two at the subatomic quantum level. There would be only two states that would be existing, and the protons would be resonating between the two states. Depending if you're giving it radio frequencies, you're making them energetic. So there would be resonance happening, and there would be an energy gap between the two. But they have to gain energy to resonate. So there's going to be an energy gap delta E, and energy is proportional to frequency. So a very specific frequency from the radio waves are absorbed by the hydrogen protons. Not any energy is absorbed. They're going to absorb exactly the right amount of energy that is proportional to frequency. So very specific frequency is absorbed. So very specific frequency is absorbed by the hydrogen protons to resonate. So it all depends. It all depends on this energy gap. This delta E could vary, and this delta E could depend on a number of factors. But is this clear as well? Okay, uh, I mean, you can't make them resonate at any frequency. It has to be the right amount of frequency. It has to be a very specific frequency. They're not going to absorb any random frequency. Okay, so every proton will choose a very specific frequency that matches with the energy that it requires to go into the opposing spin. ये भी clear है, Abu Rana, Aisha,
Yes, sir.
Ariba, clear है? अच्छा then
Yes, sir.
अच्छा then there is the fact कि अब सारी चीजें इसके ऊपर आ जाती है कि what factors affect delta E. मतलब क्योंकि everything matters on delta E कि what amount of energy is required उसी हिसाब से frequency absorb these radio waves उसी हिसाब से frequency absorb होगी. So what factors affect delta E? Because they're going to affect the frequency that's going to be absorbed. The factors affecting delta E. The number one factor is the external magnetic field. If you have a very powerful external magnetic field, the opposing spin mein jana, that's going to be very difficult. But if the magnet is really strong, this matlab hai all the hydrogen protons would be aligned. They would like to be aligned because the external magnetic field is very powerful. So it would be very hard for them to go into opposing spin. Okay? So it's going to become very hard for them to go into opposing spin. So that's the number one factor. Okay, you increase the amount of magnetic field. So greater external magnetic field so it's going to be more difficult to resonate. As it's going to be more difficult to resonate, more energy would be needed. And a higher frequency would be absorbed. Energy is proportional to frequency. So higher frequency would be absorbed. So is this factor clear to everyone?
Yes, sir.
Yes, sir.
Achha, that's the first factor. Okay, your all the protons in your hydrocarbon or whatever organic molecule, they would be aligned with the external magnetic field. And if the external magnetic field is very powerful, it would be very hard for the protons to point in the opposite direction. And they would have to become very energetic. I mean, the energy gap delta E between the high energy state and the low energy state, it's going to be a lot, which is why a very high frequency would be absorbed. Okay? Ali, clear hai?
Yes, sir.
So now the second factor. The second factor is first. I mean, the first factor is pretty pointless because you don't get any information about the molecule. Because I mean, you're the one who's controlling the external magnetic field. You increase it, the frequency that it at which it resonates, it's going to change. So the first factor is pretty pointless because you are in control of the first factor. So I mean, that's not going to give you any information. But लिख भी देते हैं, no information. No information about the molecule could possibly be extracted. Okay, so for us, the first factor is pretty useless. The second factor is the one that's important, which is the second factor, and that's known as the chemical environment. As a chemical environment, or you can call it the shielding of the proton. Now, this is the factor that actually gives you information about the environment of the hydrogen proton. Because the hydrogen proton is not existing in isolation. So think of a hydrogen proton. Okay, so you have this hydrogen proton and it has an external magnetic field and it is aligned, it has its own magnetic field and it's aligned with the external magnetic field, which is this one. So it's going from north to. So the proton is aligned, but the proton doesn't exist in isolation. It has electrons around it and it's bonded to different things. These electrons could be in orbitals and subshells around it. I mean, it is bonded with the other atoms and there are electrons that are shielding it. So what these electrons do is that these electrons kind of provide some shielding. So if there's an external magnetic field, that magnetic field could bounce off the electrons. The electrons could deflect the external magnetic field. And in that way, the proton in the middle, there's an electron surrounding the hydrogen atom, right? So the proton in the middle is not going to experience a lot of magnetic field. Why? Because it got deflected by the electron that is surrounding it. So the negative electron around the proton it deflects the external magnetic field. So imagine if it's perfectly deflecting the external magnetic field, or the amount of magnetic field experienced by the proton is very less. But all the powerful external magnetic field got deflected by the electron that was surrounding the proton. So proton experiences less magnetic field. It experiences less external and if it experiences less external magnetic field, what that would result in is that it would be easier to resonate for it. Less energy would be needed because it's not experiencing a lot of magnetic field. Is this point clear? Ali, clear? Burera?
Yes, sir.
Sarah, is this clear?
Yes, sir.
I just
I didn't understand the point. Less energy needed to resonate.
because it's not experiencing a lot of magnetic field. But वो imagine करो ना कि all the external powerful magnetic field is deflected. But think of a compass needle. Okay, the electron around it. Okay, just 1 second. So the electron around it, what it did was there was this powerful external magnetic field, right? The electron is providing the shielding. So all the external magnetic field, it got deflected in different directions by the electron that's surrounding it, right? Ali, ये बात clear है?
Okay. जी ये clear.
तो अब मुझे बताओ कि the proton is not experiencing a magnetic field. तो इसको opposite direction में point करना that's going to become very easy, right?
Oh, yes.
ठीक है, if the electron wasn't there, then the proton over there would be experiencing a lot of external magnetic field. Okay? And it would be very hard for the proton to go into the opposing spin. Is this clear as well?
Yes, sir. Sir, wouldn't it affect the proton to face towards the south?
नहीं,
The
तो
deflection.
नहीं, अपोजिंग स्पिन में जाना मुश्किल होगा ना. इट वुड बी पॉइंटिंग टुवर्ड्स द साउथ, मतलब अलाइंड होगा ना.
Same.
But it would be much harder for it to go into the opposite direction, the high energy state. ठीक है.
Okay.
So the electron around the proton, ठीक है, because the hydrogen proton doesn't exist in isolation, ठीक है. There's an electron around it as well. So if the electron is surrounding the proton, it would shield the proton. It would prevent these external magnetic fields from coming close to it, and it would experience a lesser amount of external magnetic field. ठीक है. The electron would deflect a lot of these external magnetic fields. So the proton would experience less magnetic field, and it would be easier for it to go into the opposing spin by gaining energy and going into the opposite spin. It would become much easier for it. ठीक है. और imagine करो कि there is no field, फिर zero energy would be required. The proton can freely point in any direction. ठीक है. Think of a compass needle. अगर Earth की external magnetic field ना होती तो the compass could point in any direction it likes, right? चलो ये लास्ट वाले पॉइंट है ना, ये तो अभी हमने स्टार्ट किया था. We'll continue next class with the last point. ठीक है. We'll discuss the last point in detail again in the next class. ठीक है.
Okay, sir. Love it.
Okay. ठीक है.
Okay, sir, can you forward me the board link?
ठीक है. बोर्ड लिंक में कर देता हूँ. ये मैं भेज दिया. ठीक है.
ठीक है, okay. खुदा हाफिज.
Okay.